How far is too far when you stop talking about planets and start talking about stars? The closest star system you can actually aim at, Proxima Centauri, sits about 4.24 light years away. 1 light year is how far light travels in a year, at 300,000 kilometers per second. So when you multiply that out, you get roughly 40 trillion kilometers, around 25 trillion miles. That's not far in the way a long road trip is far. That's far in the sense that normal human distance instincts just stop working. You're outside the range your brain evolved for. But before we continue, please subscribe to the channel to give your support. Let's continue. Now, put a very simple test on that distance and keep it brutally honest. Take a steady highway speed, around 100 kilometers per hour, about 60 miles per hour, something your car can do all day. Keep that speed constant. No traffic, no fuel stops, no breakdowns, just a perfect cruise. At that speed, the trip to Proxima Centauri would take on the order of 4.5 billion years. That number is not random. That's about the age of Earth itself. So if you left when the planet formed, you'd be arriving roughly now. That's your first hard wall. The raw distance between stars is not just large, it is on the same scale as the entire history of your planet. You might push back and say, fine, cars are slow, but we build things way faster than that. Rockets are insane compared to a car, so doesn't that fix it? That's the next layer of the problem. Right now, the speed record for any human-made object belongs to the Parker Solar Probe. By diving close to the sun and using gravity assists, it reaches about 190 kilometers per second, which is roughly 430,000 miles per hour. Compared to everyday experience, that speed is absurd. In a single second, it covers almost the distance from London to Paris. On Earth, nothing you ever ride or drive even comes close to that regime. So take that world record speed and see what it does against the Proxima distance. Run the numbers. Keep the assumptions simple. Straight line, constant top speed. No slowing down until you get there. Even then, you're looking at a travel time of around 7,700 years. That's 67 centuries. If some ancient civilization had somehow launched a Parker-class probe back in the Bronze Age, it would still be in transit now, nowhere near the end of its journey. The fastest machine humans have ever built is still thousands of years away from making an interstellar trip to the nearest star. If the absolute record holder needs millennia, it's fair to ask, what about the hardware that's actually heading out of the solar system today? The stuff we point to when we say we're already interstellar. Look at Voyager 1, because it quietly shows you how slow this really is. Voyager 1 launched in 1977, and today it's traveling at about 17 kilometers per second, around 38,000 miles per hour. That's still very fast on human scales. It would cross a continent in a few minutes, but in cosmic terms, it's modest. After almost 50 years of continuous flight, it's only about 24 billion kilometers from the sun, roughly 15 billion miles. On a light-year scale, that's about 0.0025 light-years, not even 1% of the distance to Proxima Centauri. It's a few thousandths of the way to the nearest star. If you extend Voyager's current speed all the way to Proxima, you get a travel time of about 75,000 years. That's older than agriculture, older than recorded history, older than cities. That's a timescale where human cultures change completely. Languages vanish. Entire civilizations rise and fall, while one probe just keeps coasting. So when people say, we've already entered interstellar space, technically that's true. But in terms of going from one star to another, we are still crawling. Any human mission that wants to be taken seriously as interstellar has to shred that 75,000-year number down to a human lifetime or less. You are not talking about going twice as fast. You're talking about jumps of 100 times, 1,000 times in effective mission speed. At this point, a natural reaction is, all right, then we just need to get close to light speed. That's the real goal. So how does that change the picture? Light is your hard benchmark here. It moves at about 300,000 kilometers per second, 186,000 miles per second. At that speed, a signal from Earth reaches the moon in just over a second. It crosses the distance to Pluto in about 5 hours. That's your absolute speed limit for information and for anything without mass. Even at that maximum, getting from the Sun to Proxima Centauri takes a little over 4 years. So the universe is basically saying, even with the best possible speed, this is not a weekend trip. When people talk about starships going at 10% of light speed, they're talking about something like 30,000 kilometers per second, about 67 million miles per hour. At that speed, the flight time to Proxima is on the order of 40 years, plus extra time to ramp up to that speed and extra time to slow down at the other end. Now you're in a range where a human could, in principle, leave as an adult and still be alive at arrival, especially if medicine extends lifespans. But getting a real spacecraft with people, shielding, supplies, and backup systems up to 10% of light speed is not a small upgrade from Parker's 190 kilometers per second. It is a completely different level of energy, engineering, and reliability. So after looking at cars, rockets, record-breaking probes, and even the speed of light, what does all this say about your original question? When will humans achieve interstellar travel? It tells you that the timeline isn't driven first by exotic biology or clever mission planning or even cool sci-fi tech names. It's driven by one hard requirement. How soon can you cover about 4 light years in less than a human lifetime? Right now, with Voyager-class speeds, that trip takes tens of thousands of years. With Parker-class speeds, it's still thousands of years. With 10% of light speed, it drops into the range of decades, which is finally usable for an actual crew that expects to arrive before old age. To make that jump, you need to cut our effective interstellar travel time by roughly 3 orders of magnitude compared to the probes we have now. You need to take 75,000 years and turn it into something like 70 years, including acceleration and braking. Until your propulsion, your energy systems, and your ship reliability can handle that kind of speed and duration, human interstellar travel is not on the near-term calendar. It's locked behind huge engineering and energy barriers. So the next step is to ask a much sharper, more practical question. Given how extreme these numbers are, where are we actually starting from right now with the real spacecraft and space stations we've already built? And how primitive does that look when you measure it against the distance to the stars? You've probably heard people say, we've already gone interstellar, Voyager's out there in the stars. That sounds impressive, but here's the blunt reality. Our entire interstellar hardware fleet is 5 tiny robots, all of them old, all of them slow on star scales, and none of them remotely close to another star. Right now, only 5 spacecraft are actually on escape paths out of the solar system. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and New Horizons. That's it. Not swarms, not armadas, just 5. Their speeds sit in the range of about 12 to 17 kilometers per second, so roughly 43,000 to 61,000 kilometers per hour, about 27,000 to 38,000 miles per hour. If you dropped one over Earth, it would cross a continent in minutes. But in the context of interstellar space, those numbers are low. These craft are uncrewed, powered by slow-decaying nuclear batteries and built with 1970s to 2000s electronics. They are like early metal tools compared to steel skyscrapers. Useful, historic, but clearly primitive when you think about building a starship. So here's the tension. If even our best outbound machines are this rare and this limited, what happens when you ask a bigger question? Not, are we leaving the solar system, but how far into it are we actually getting? Take the Oort cloud, the distant shell of icy bodies that probably surrounds the solar system. It may extend out to about 100,000 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, around 150 million kilometers, about 93 million miles. Multiply that by 100,000 and you get roughly 1.5 times 10 to the 13 kilometers, around 9 trillion miles. That's still not another star. That's just the outer edge of the Sun's own gravitational territory. Now plug our escape probes into that. At 12 to 17 kilometers per second, you're talking tens of thousands of years just to reach the outer Oort cloud. Not the next star, not a new sun in the sky, just the dim edge of our own system's debris field. So when you step back and look at the map honestly, you're not almost at the stars, you're barely past the doorway. This is the level of technology you're starting from when you ask, when do humans actually travel between stars? But if these probes are that slow and that limited, why do scientists care so much about them when they talk about interstellar travel timelines? Because they are the first real data points on what very long missions actually do to hardware. Look at Voyager 1 again. It's about 24 billion kilometers from the sun now, around 15 billion miles. Its power source, a radioisotope generator, has been fading for decades. Instruments are being shut down one by one to save power. Sensors fail, electronics suffer radiation damage, glitches show up that nobody saw in testing on the ground. Even the radio link is right on the edge. By the time its signal reaches Earth, it's far weaker than the Wi-Fi from a cheap home router, and that's after you collect it with huge antennas. Now scale that up to 4 light years. The distance is more than 100 times larger. The travel time for a slow probe jumps from decades to thousands of years. The signal gets absurdly weaker. Your antennas need to be better, your power needs to last longer, your fault tolerance has to be stronger. If a 50-year mission already pushes our gear to the limit, a mission that lasts centuries or millennia is basically off the table with current designs. So Voyager and its cousins are not just cool science missions. They are hard reality checks for what long duration actually means in deep space. If the robots are struggling after a few decades and a few dozen astronomical units, what happens when you add humans to the story? On the crewed side, your current benchmark isn't some sleek starship. It's the International Space Station, orbiting at about 400 kilometers up, roughly 250 miles. That is still inside Earth's protective magnetosphere, still just above the atmosphere, still within easy reach of regular cargo runs. The longest continuous stays there are on the order of a year or so. Even in that relatively safe and supported environment, astronauts come back with noticeable muscle loss, lower bone density, radiation exposure issues, and sometimes vision problems. They exercise for hours every day, they are monitored constantly, and it still hits their bodies hard. Now compare that to what you need for an interstellar trip, multi-decade missions, maybe moving at a significant fraction of light speed, billions and billions of kilometers away from the sun's magnetic shield, with no quick rescue options, no fast resupply. You would need artificial gravity, probably by spinning a big habitat to simulate 1G, or at least something close. You would need far heavier radiation shielding, meters of water or other material. You would need closed life support systems that recycle almost everything, with almost no margin for failure. Right now, your biology is barely tolerating low Earth orbit. Your medical data for deep space is thin. So if you're honest, you have to say you're not a starship species, you're a space station species. So if the robots are weak on the timescales you need, and the human body is still tuned for low orbit and short missions, does that mean this whole era is just dead weight? Just a prelude you can ignore when talking about interstellar timelines? No, this era is exactly why you can make any serious prediction at all. Call it the Interstellar Bronze Age. Early, rough, limited, but critical. These missions tell you how electronics age in radiation over decades, how power systems fade, how often things glitch, and what it takes to talk to something that far away. The ISS and other crewed flights tell you what microgravity and space radiation do to human bodies in months and years, not just weeks. Every failure mode, every unexpected behavior, every "we didn't think of that" becomes a constraint for the next generation. So when you ask, when will humans achieve interstellar travel, you can't pretend you're starting from zero, and you also can't pretend you're already advanced. You have to assume at least 2 or 3 big technology generations beyond Voyager for uncrewed interstellar probes, and at least that many beyond the ISS for crewed deep space habitats. That already pushes any realistic prototype interstellar probe well into the late 21st century or beyond. And that's just for small, uncrewed scouts. For a human mission, you're looking at another step up in reliability, energy, and life support. And there's an extra twist here. Even if you solve the engineering problems, there's a deeper wall waiting for you, a limit written into the structure of space and time itself. So if this is the Bronze Age, still slow and fragile, what happens to your timeline when you add the next brutal constraint? The fact that physics itself sets a hard speed limit you can never cross, no matter how advanced you get. You've seen how bad the distances are, but there's a second punch coming. The universe doesn't just put the stars far away, it also caps how fast you're allowed to go to reach them. Here's the next problem. The universe has a built-in speed limit, and you don't get to cheat it. According to special relativity, anything that has mass can never reach the speed of light. The closer you push a ship towards light speed, the more its energy needs go through the roof. In simple terms, as your speed creeps up to that limit, each extra bit of speed costs more energy than the last bit. By the time you're at 90% of light speed, the factor that describes this relativistic load on your ship is already more than double what it is at low speed. That means your engines aren't just working harder, they're paying a brutal premium for every extra percent of speed. So in real engineering, you're not going to see human starships doing 90 or 99% of light speed anytime soon. Long before that, you run into insane fuel demands, ridiculous waste heat, and shielding problems, because even a grain of dust hitting you at those speeds carries rifle-like energy. Most serious concepts hover in a range like 10 to maybe 30% of light speed, between 0.1 and 0.3 in units of light speed. That still sounds huge compared to today, but it's already pushing the edge of what engines, structure, and shielding can even begin to handle. If you can't reach light speed and you don't want to spend millennia in transit, is there any trick left that actually helps you, or are you just stuck with these giant calendar times? Here's the weird part. When you push close to light speed, time stops behaving the way you expect. This is time dilation. From the point of view of someone watching you from Earth, your ship takes, say, 20 or 30 years to crawl to the nearest star at a high fraction of light speed. But from your point of view on the ship, the clocks run differently. Your own time stretches out in a different way compared to the outside universe. At around 90% of light speed, a trip that looks like roughly 20 plus years on Earth can feel only about 10 years on board. To you, your heart, your watch, your aging body, the journey feels much shorter than the outside world measures. That sounds like a cheat code, but it has a catch. Time dilation helps the crew feel less time passing. It does not make the mission shorter on the calendar back home. Earth still waits those full decades for news. People on the ground still see a mission that starts in one generation and finishes in another. So yes, time dilation is a powerful effect, and it might be the thing that makes ultra-fast missions psychologically tolerable for the people on board. But it does not fix the deeper question: how much energy do you have to put into a ship to get anywhere near those speeds in the first place? So if time dilation is the only relief, what does the energy bill look like when you try to push even a modest starship to 10% of light speed? Now the bill shows up, and it's ugly. The kinetic energy of a moving object, the energy it has just because it's moving, depends on its mass and on the square of its speed. That squared word is the killer. If you double the speed, the energy goes up by 4 times. If you multiply the speed by 10, the energy shoots up by a factor of 100. For interstellar flight, you're not multiplying your speed by 10, you're talking about multiplying it by thousands compared to normal rockets. Take a very conservative interstellar ship. 1,000,000 kilograms, which is 1,000 metric tons. That's heavy, but not crazy for something that has people, shielding, life support, and structure. Now, aim for 10% of light speed, around 30,000 kilometers per second, about 67 million miles per hour. When you work through the numbers, the kinetic energy you need to give that ship is on the order of a few times 10 to the power 20 joules. For reference, all of humanity today uses something like 6 times 10 to the power 20 joules of primary energy in an entire year. So just to accelerate that single ship to 10% of light speed, without even thinking about slowing it down at the destination, you're already in the same league as the total annual energy output of our whole civilization. And remember, you have to brake at the other end unless you want to scream through the target system and never stop. That means you either pay that energy bill twice, once to speed up, once to slow down, or you invent some clever method that lets you dump that energy into something else, like a magnetic sail interacting with the interstellar medium. Either way, the bottom line is simple. Fast interstellar flight is not a bigger rocket problem. It's a civilization-scale energy budget problem. Even if you had that much energy, you'd still have another question to answer. What happens to all the waste heat from those engines while you're pushing that hard for that long? The universe has another quiet rule. Big power means big heat. And in space, getting rid of heat is slow and painful. On Earth, you can blow hot air into the atmosphere or dump heat into water. In space, there is nothing to blow it into. The only way to cool a ship is to radiate heat away as infrared light. The power you can radiate depends on how hot your radiators are and how big their surface area is. If you are running engines that are pushing gigawatts or even terawatts of power, which high-speed starships will likely need, a big fraction of that power turns into waste heat that has to go somewhere. That means huge radiators, structures stretching maybe hundreds of meters or even kilometers across, glowing hot in the infrared, constantly dumping energy into space. But those radiators have mass, and extra mass means you need more energy to accelerate, which means more heat, which means bigger radiators. You get a loop. More power, more heat, more mass, more power again. At some point, this loop sets a practical ceiling on how fast a real ship can run its engines without cooking itself. So the timeline for interstellar travel is not just about when you get a powerful drive, it's about when you can build a system that handles the heat from that drive without tearing itself apart or melting key components. Put all of this together and you hit the real shape of the problem. Relativity is not telling you no, it's telling you pay up or slow down. Relativity says you cannot go faster than light, and it makes the energy cost for high fractions of light speed rise sharply as you get closer to that limit. Time dilation throws you a bone by letting the crew experience less time, but it does nothing to shrink the mission for the rest of humanity. The energy numbers tell you that even a modest 1,000-ton starship at 10% of light speed demands a year-scale slice of our entire current global energy use just for acceleration, never mind braking. The waste heat problem tells you your engines and radiators have to be part of a giant, massively engineered thermal system, not just a motor and tank. So when you ask when will humans achieve interstellar travel, relativity quietly sets the boundary conditions. Fast, crewed interstellar flight only becomes believable when human civilization can throw terawatt to petawatt levels of sustained power at a single mission, and can build machines that manage that energy and heat safely for years. That is not where we are in 2030. It is almost certainly not where we will be by 2100. You're talking about an era where energy production, space industry, and engineering are operating at a whole new level. And here's the kicker. Even before you run into all these relativistic headaches, there's another law of physics waiting closer to home, the rocket equation, which punishes any design that tries to carry all its own propellant. So if the universe is already charging this much just for speed, what happens when the math of rockets itself tells you that chemical propulsion is a dead end for starflight? Relativity gives you a hard speed limit, but there's another piece of physics that kills just build a bigger rocket ideas even earlier, the rocket equation. Any rocket that carries its own propellant is stuck with a tight relationship between how fast the exhaust comes out the back, how much mass you start with, including fuel, and how much is left once the fuel is gone. That speed change you can get depends on the exhaust speed multiplied by a logarithm of that mass ratio, start mass divided by final mass. That word logarithm means you hit diminishing returns fast. To squeeze out more total speed, you don't just add fuel in a straight line, you have to add more and more for each extra chunk of speed. Past a certain point, every extra bit of velocity demands a huge amount of extra propellant. Push it hard enough and you cross into the impossible zone. You'd need more fuel than you can physically pack into any realistic rocket, even if the whole ship was basically just tanks. So if chemical rockets hit a wall that early, what about the biggest launchers we've already flown? Do they get you any closer to what you need for interstellar trips? Look at the Saturn V, the rocket that sent Apollo to the moon. Its total change in speed from liftoff to sending the spacecraft toward the moon was around 10.8 kilometers per second, about 24,000 miles per hour. Modern heavy lift rockets are in the same general zone, maybe a bit more efficient, but nowhere near orders of magnitude better. That's enough to climb out of Earth's gravity well and head to the moon or the outer planets, but it's nowhere near what you need for interstellar flight. To send a ship to another star in less than a human lifetime, you want speeds that are thousands of times higher than a moon mission. No amount of strapping extra boosters to a Saturn-class rocket gets you that kind of jump. The rocket equation is yelling at you. This model stops working here. The idea of carrying all your propellant in tanks attached to your vehicle simply does not scale to starflight. So, if more thrust and more stages on chemical rockets won't fix it, what actually limits their performance? Why can't we just make them more efficient? That's where specific impulse comes in. It's a measure of how efficiently a rocket engine turns propellant into thrust. You can think of it as how many seconds this engine can push per unit of fuel. Higher specific impulse means better performance. Chemical engines top out at around 450 seconds in vacuum for advanced designs, like the old Space Shuttle main engine. Nuclear thermal engines, where a reactor heats hydrogen and blasts it out the nozzle, might reach something like 800 to 1,000 seconds. That's already a factor of 2, and it's great for faster trips to Mars. But for practical interstellar travel where you want to cross 4 light years in decades instead of millennia, you're not looking for a factor of 2, you're looking for a factor of 50 to 100 in effective specific impulse. That points straight at fusion, or at propulsion systems where you don't carry most of the fuel with you, like giant laser beams pushing a sail. You might argue, staging worked for Apollo. Just add more stages, drop empty tanks, and keep going. Doesn't that hack the rocket equation a bit? It helps, but not in the way you need. Staging is simple. You stack multiple rocket segments, and when one runs out of propellant, you drop the empty hardware to lose dead weight, then light the next one. This multiplies the effective change in speed because each stage has its own mass ratio. That's how we got to orbit and to the moon. But even with multi-stage designs, you're still fighting exponential math. Each stage gives you a limited boost, and the gains stack, but they do not suddenly leap by factors of 1,000. You might squeeze out a factor of 2 or 3 in total speed over a single stage design with the same technology. That's enough to move around inside a solar system more efficiently, but it doesn't get you anywhere near 10% of light speed. There is a point where more stages just means more complexity and more cost without ever breaking you out of the constraints set by the underlying equation. So, what does all of this actually say about your original question? Not in theory, but in terms of real timelines for when humans might go interstellar. It says something harsh. Human interstellar travel does not start in the chemical rocket era, and probably not in the classic rocket plus tanks era at all. As long as your propulsion concept is carry all your propellant and throw it out the back, you stay chained to the rocket equation, and it punishes you as soon as you ask for star-level speeds. To move into the interstellar age, you need a phase change in propulsion, not an incremental upgrade. That means switching to much higher energy reactions like nuclear fission and especially fusion, or switching to systems where the energy source and propellant are mostly external to the ship, like giant laser arrays driving light sails. That requirement alone pushes the realistic timeline for crewed interstellar travel far beyond the period where we're just improving chemical launchers and building bigger reusable rockets. First, you have to climb a new ladder of technology into nuclear, fusion, beamed power. Only once those are mature do you start to talk about putting humans on something heading for another star. And that raises the next question. If chemical propulsion is a dead end and pure rocket staging can't save you, what does the first step beyond that look like? What happens when you bring nuclear fire into the picture and try to turn reactors and even nuclear explosions into Starship engines? At what point does more powerful stop meaning strap on extra tanks and start meaning change the kind of fire you're using? That line is basically where nuclear propulsion shows up, the first serious step beyond chemical rockets, and the first time you can even say the words interstellar without laughing. Nuclear thermal rockets are the simple version of that shift. Instead of burning fuel and oxidizer in a chemical reaction, you run hydrogen through a nuclear reactor, heat it up to extreme temperatures, and throw that super hot gas out the back as exhaust. Because the energy per kilogram in nuclear fuel is so much higher than in chemical fuel, you can get exhaust that is a lot more energetic. In practice, designs like this can roughly double the efficiency number that rocket engineers care about compared to the best chemical engines. That means instead of topping out around 450 seconds of specific impulse in vacuum, you're looking at around 800 to 900 seconds. Translated into everyday terms, that means the same amount of propellant can give you roughly twice the total push over time. For missions inside the solar system, that is a big deal. A Mars trip that takes many months with chemical stages could shrink to something more like weeks to a couple of months with a well-designed nuclear thermal stage. That's the difference between crew spends most of a year in transit and crew spends a much smaller fraction of their mission just coasting. But interstellar distances don't care about that kind of tweak. Doubling your performance still leaves you in the range of tens of kilometers per second, not thousands. You go from very slow compared to light to still incredibly slow compared to light. So nuclear thermal rockets are important, but they are warm-up technology for interstellar travel, not the main engine. If nuclear reactors pushing hot hydrogen still leave you crawling on star scales, what happens if you stop being gentle and start using the most violent nuclear devices we've ever built as your engine? That's where Project Orion comes in, the most extreme, this might actually work propulsion idea anyone has ever put serious engineering into. Back in the 1950s and 1960s, engineers and physicists looked at nuclear bombs and said, what if a ship rode the shockwaves? The design was simple in concept and insane in execution. You put a huge metal plate, a pusher plate, on the back of a spacecraft. You eject small nuclear bombs behind the ship, set them off, and let the blast hit the plate. Massive shock absorbers between the plate and the rest of the ship smooth out the kicks. Each explosion gives the ship a tiny boost. Do this thousands or millions of times and the boosts add up. On paper, this approach could throw around ships that are not just a few tons, but millions of tons. That's enough mass for real habitats, shielding, supplies, everything. And the potential top speed is in a different class from chemical or even simple nuclear thermal rockets. Depending on the exact design and how aggressive you are with the bombs, Orion-style propulsion could reach a few percent of light speed, maybe around 3%. That's about 0.03 times light speed, roughly 9,000 kilometers per second, close to 20 million miles per hour. At that speed, the nearest stars are still decades away, but you finally moved out of the tens of thousands of years regime into timescales that at least make sense for long robotic missions. So if Orion-style bomb propulsion looks like one of the only ways, using technology you can at least imagine building, to reach a few percent of light speed, why isn't everyone working on it right now? To answer that, you have to look at why nuclear is tempting in the first place, and then what ugly problems come with that temptation. Nuclear fission fields like uranium hold a ridiculous amount of energy per kilogram. Split a kilogram of uranium in a reactor and you release on the order of 10 to the power 13 joules. That's roughly 10 million times more energy than you get from a kilogram of typical chemical propellant. In rocket terms, that means you can get a lot more push per unit of reaction mass, so your mass ratios don't explode as badly as they do with chemical fuel. The rocket equation is still there, but it bites less hard. However, even with nuclear, you still have to carry the reaction mass you throw out the back, and in many designs, you're also carrying the fuel that powers the nuclear reactions. You're also dealing with huge amounts of waste heat from the reactor or the explosions, and intense radiation fields near the engines, which means heavy shielding to protect the crew and sensitive electronics, which means more mass, which means more energy needed to accelerate the ship. So nuclear energy density makes the problem less impossible, but it doesn't magically erase the fundamental issues of heat, shielding, and mass. And that's before you talk about what it actually means in environmental terms to launch and run a ship that is literally firing nuclear bombs behind it every few seconds. Modern treaties, public opinion, and basic environmental sanity all slam into Orion-style ideas hard. Detaining thousands of nuclear devices in space, even if you do it far from Earth, throws radioactive debris into trajectories you can't perfectly control. Any launch failure on the pad or in low orbit while you're still carrying a large number of nuclear devices would be a disaster. Even nuclear thermal rockets that only use sealed reactors without explosive pulses face strong regulatory resistance. People are worried, with reason, about what happens if a launch vehicle carrying a reactor breaks up in the atmosphere, or if long-term contamination in orbit becomes an issue. So the real timeline for large-scale nuclear propulsion isn't just when will the hardware be ready, it's when will global civilization be stable, coordinated, and desperate enough to accept the risk. That likely means a future where space infrastructure is already huge, energy demand is massive, and the benefits of going faster are seen as critical. You're probably talking about the late 21st century at the earliest for any serious push on high-power nuclear propulsion in space. Even if you imagine a future where treaties get updated and people accept nuclear engines in space, you still have the question, does nuclear actually get you all the way to practical human starflight? Or is it just a stepping stone? The honest answer is that nuclear is a bridge, not the end of the road. Nuclear thermal engines could give you faster crewed trips to Mars and the outer planets. Nuclear pulse designs, whether classic Orion or more refined versions with smaller pulses, might let you send uncrewed probes to the nearest stars in a few hundred years of flight time instead of tens of thousands. That is a huge improvement. Going from 75,000 years to a few centuries changes the entire character of interstellar exploration for machines. And if advanced nuclear pulse systems reach a few percent of light speed, star probes launched in, say, the 22nd or 23rd century could arrive within a human historical attention span, even if no individual human lives through the whole mission. But for crewed missions to another star where people expect to arrive within their own extended lifetime, nuclear as we currently imagine it is still short of the mark. A few percent of light speed means travel times of more than a century to the nearest stars. That's generation ship territory, where the great-grandchildren of the launch crew reach the destination. That kind of mission is possible in principle, but it's a huge jump in social complexity and risk. To get travel times down to the range of a few decades for humans, you want speeds closer to 10 or 20% of light speed, and that leans more towards fusion drives or beamed sail systems than classic nuclear-based nuclear designs. So nuclear propulsion looks like the first real break away from the chemical rocket era, the first bridge technology that could make interstellar probes a serious engineering project instead of a fantasy. But that also sets up the next challenge. If nuclear is just the bridge, what kind of engine sits on the far side of that bridge, powerful enough to push starships to a significant fraction of light speed without tearing them apart or burying them in impossible fuel loads? What happens when you stop burning chemicals and start using the same basic process that powers stars? That's the point where fusion drives enter the story, and for the first time, the numbers for interstellar speed start to look like something other than a bad joke. Fusion is what happens when light nuclei, like forms of hydrogen, smash together and merge into heavier nuclei, releasing huge amounts of energy per kilogram of fuel. That's another giant step up from fission, which was already millions times better than chemical propellant. With that kind of energy density, you can finally talk about starship designs that reach a tenth of light speed, not in fantasy, but in rough engineering studies. That's what Project Daedalus tried to do on paper. The design was a two-stage fusion-powered ship using pellets of deuterium and helium-3 as fuel. The idea was to push a payload of around 450 metric tons, so something in the range of a large spacecraft or a small station, up to about 12% of light speed, roughly 0.12 c. At that speed, a trip to a nearby star like Barnard's star would take around 50 years of ship time. Suddenly, you're not talking tens of thousands of years like Voyager, you're in the zone of one long human lifetime for the mission, at least from the ship's point of view. So if the paper numbers look that good, and we already know fusion works in stars and in bombs, why don't we have fusion starships on the drawing board in real life today? Because right now, even building a fusion power plant that just sits still on Earth is a serious struggle. Experimental reactors like tokamaks and stellarators are only just reaching or getting close to net energy break-even, and even then only in very short bursts. You have to hold a plasma at temperatures of hundreds of millions of degrees, hotter than the core of the sun, and keep it confined away from any material walls. On Earth, that already needs giant magnets, heavy structures, complex control systems, and everything still lives inside a building with constant human maintenance. Now take that and move it into deep space and ask it to work not for a few seconds in a lab, but for years or decades in a vacuum with no maintenance team nearby while also providing directed thrust. Turning fusion from big experimental machine plugged into the grid into reliable, lightweight, pulsed rocket engine that runs for decades is not a single step. It's several full revolutions of technology beyond where we are. Even if you assume we eventually get good at controlled fusion on Earth, the way you use it for propulsion is its own nightmare. Project Daedalus and similar designs rely on something called inertial confinement fusion. Instead of holding one big plasma in place with magnets, you fire tiny fuel pellets into a chamber at high speed, then hit each one with intense beams from lasers or electron guns to crush and heat it so fast that it fuses before it can blow apart. Each pellet goes off like a microscopic fusion explosion, and the hot plasma pushes against magnetic fields or a physical nozzle to create thrust. The engineering requirements are brutal. You're talking about firing maybe hundreds of thousands to millions of fuel pellets every second for long periods with incredibly precise timing and alignment. Every pellet has to be manufactured to exact specifications. The beams that trigger them have to be stable and reliable. The reaction chamber walls or the magnetic fields standing in for walls have to handle that constant hammering without failing. Any defect in the fuel stream, any misfire, any buildup of damage over time could wreck the engine. That level of industrial precision and automation at that speed for that long is way beyond what our current factories and robotics can handle. And then there's the fuel itself. Some of the more attractive fusion reactions use helium-3 because it can produce fewer problematic neutrons and less radiation damage to your engine. But helium-3 is incredibly rare on Earth. You can't just dig it out of the ground in bulk the way you dig up coal or uranium. The more realistic sources are in the atmospheres of gas giants like Jupiter and Saturn, where trace amounts of helium-3 exist mixed into vast quantities of hydrogen and normal helium. That means that before you even think about building a Daedalus-style ship, you need to build a whole industrial phase just to gather its fuel. You'd have to send heavy, robust craft into the upper atmospheres of gas giants, scoop up enormous masses of gas, separate out the helium-3 in giant processing facilities, then haul it back out of those deep gravity wells into orbit, and finally ship it to your Starship construction sites. That is a multi-decade, maybe multi-century program on its own, involving fleets of mining vehicles and refineries. And that's all before you start welding together the first real interstellar vehicle. So with all those problems, how do you even talk about timelines for fusion drives, both for power on Earth and for engines in space? Right now, fusion research is making progress, but it's slow and messy. If things go well, a reasonable guess is that the first practical commercial fusion power plants on Earth might show up near the end of this century. That would already be a huge win for energy and climate, and it would prove that we can tame fusion in a controlled, predictable way for long periods. Once you have that, the path to using fusion in space starts to open up, but it won't be immediate. You still need new designs that are lighter, more robust, and optimized for thrust, not just electricity. If you extend that line out, fusion-powered deep space probes still inside the solar system or heading slowly toward the outer regions might appear sometime in the 22nd century. Those would be testbeds for long-duration fusion systems running for years, maybe decades. After you have that experience, fusion-driven interstellar probes aiming for speeds like 10 or 20% of light become realistic projects probably in the 22nd or 23rd century. These first interstellar fusion probes would almost certainly be uncrewed, robotic scouts, because you don't risk human lives on the very first full-scale tests of such a complex propulsion system. Crewed fusion starships, where people actually ride along at a good fraction of light speed, are another step beyond that. You need not just reliable fusion engines, but also mature closed life support, radiation shielding that works for decades, artificial gravity, and a civilization rich and stable enough to throw enormous energy and material resources at a single mission. Under optimistic but still grounded assumptions, that pushes crewed fusion starships into the 23rd century and beyond, and that's assuming no major collapse of technology or global order along the way. So, fusion looks like the first propulsion method that can seriously hit the speeds you want for human timescale interstellar travel, but it's also clearly not a near-future toy. It sits on top of a chain of other progress, from fusion power plants on Earth to space industry around gas giants to high-precision automated manufacturing in orbit. And then there's a still deeper question. If carrying any kind of fuel, chemical, fission, or fusion, always drags you back into mass and rocket equation problems, what happens if you flip the script and let almost all the energy stay back home, firing across space as light, while tiny ultralight star probes ride that beam like bullets? How do you get around the rocket equation without rewriting physics? One answer is brutal and clever. You stop carrying your propellant. You leave almost all the energy and fuel at home, and you push the ship with light itself. That's the core of Breakthrough Starshot. The idea is to build gram-scale probes. Think a few grams of electronics and sensors attached to light sails a few meters across. On the ground, or maybe in orbit, you build an array of lasers adding up to around 100 gigawatts of power. For comparison, that's about the output of 100 large nuclear power plants, all focused into one combined beam. You hit the sail with that beam hard for a short period. The momentum from the photons pushes the sail, and because the payload is so tiny, the acceleration is extreme. Target cruise speed? Roughly 0.2 times the speed of light, around 60,000 kilometers per second, about 134 million miles per hour. At that speed, a probe could cross the 4.24 light years to Proxima Centauri in around 20 years of flight time. Add a few years for data to get back, and you still fit the whole mission inside a single human career. That's the first concept on the table that takes nearest star in one generation and backs it with numbers that at least roughly close. If the trick is leaving the fuel behind and pushing with photons, what does that really change compared to rockets and fusion drives? The key move is that you stop treating the ship as a big fuel tank. In Starshot-style concepts, the probe carries almost no propellant. Its job is simply to be light and reflective. The real engine is the massive laser array back home. Photons carry momentum, even though they're massless, and when they bounce off the sail, they transfer that momentum, giving a push. Because the ship isn't carrying thousands of tons of fuel, the rocket equation, with its punishing logarithm of mass ratio, no longer dominates your delta V, your total speed change. Your limit is now how much power you can pour into the beam, how well you can keep that beam on target, and how strong and reflective your sail material is. There's a trade-off, and it's extreme. With a gram-scale payload, the same push produces huge acceleration, not gentle airplane-style 1g, but tens of thousands of g. That's acceleration so strong it would turn a human into paste instantly. But a tiny solid-state probe with no fragile body, no liquids, no moving organs can survive accelerations that would destroy a person. That's why Starshot is uncrewed by design. You don't slowly ramp up to 0.2 C over months. You slam the sail hard for minutes or hours, let it rip, then coast for decades through interstellar space with no more propulsion. If you're going to push something to point 2C with light, the obvious question is, what does the laser side of this system actually look like, and how hard is that to build? A 100 gigawatt laser system is not just a bigger version of the laser pointer on a keychain. It's an entire piece of planetary infrastructure. First, you need to generate that much power, which means tapping into an energy source on the order of 100 gigawatts just for the array while it's firing. That likely means a mix of massive solar farms, big fusion or fission plants, or both. Then you need thousands or millions of smaller laser units arranged in a phased array over kilometers of land or in orbit. All of them must fire in sync so that their beams combine into one tightly focused beam. On top of that, you have to deal with Earth's atmosphere if the array is on the ground. Air distorts and scatters light, especially at high power, so you need adaptive optics, systems that constantly adjust mirror shapes and phases to correct for atmospheric turbulence in real time, like the tech used on advanced telescopes but scaled up massively. As the sail races away and its angle in the sky changes, the array has to track it perfectly, keeping the beam on a target that is shrinking and accelerating. This is not a big lab in the desert problem. This is a national or global mega project problem, in the same category as building entire power grids or giant space telescopes. Even if you can build the laser array, the sail itself has to survive conditions that are way beyond normal materials. So what kind of sail can handle that? When you hit a sail with a 100 gigawatt beam and try to push it to 0.2C, the photon pressure and heating become brutal. Every bit of light that isn't perfectly reflected turns into heat inside the material. If the sail absorbs too much, it melts or rips. If it's too heavy, it doesn't accelerate fast enough. So you need a material with incredibly low mass per square meter, almost like a sheet of nothing, plus reflectivity near 100% at the laser wavelength, and high tolerance for temperature. On top of that, it has to hold together under huge accelerations without tearing or buckling. Researchers are experimenting with nanostructured materials and metamaterials, where you engineer the structure at the nanoscale to control how light interacts with it. You can tune these structures to reflect specific wavelengths very efficiently. Some early lab results are promising, showing ultra-thin films with surprising strength and optical properties. But scaling that to large, flawless, meter-scale sails and then pushing those sails with multi-gigawatt beams is another level. This is cutting-edge material science. Not fantasy, but it's nowhere near ready to fly to another star today. So you can see a path where the physics works and the engineering is tough but not impossible, which raises the next issue. When could we actually see real hardware using this approach? And does any of that help with sending humans? Beam sails are almost guaranteed to start uncrewed and stay uncrewed for a long time. The very thing that makes them powerful, insane acceleration on lightweight probes, makes them lethal to human passengers. A person can tolerate maybe a few G for limited periods, maybe 10 G in extreme situations. Starshot level designs talk about tens of thousands of G. There's no way to soften that without also throwing away the main advantage of the system. So the first practical use case is small probes. Tiny chips with cameras, magnetometers, maybe some basic instruments, firing off toward nearby stars. A realistic sequence might look like this. Late in the 21st century, if energy infrastructure and laser tech keep advancing, you could see in-system tests, pushing small sails around the solar system at sub-relativistic speeds, maybe hundreds or thousands of kilometers per second. Those missions would prove out the basic beam control, sail materials, and guidance. If that works, a full Starshot-style attempt to Proxima Centauri or another nearby target might follow in the late 21st century or early 22nd century. Travel time would be on the order of 20 years, plus another 4 years for the first signals to get back. For humans, the impact is indirect but huge. You would get detailed close-up data on nearby star systems, including planetary atmospheres and environmental conditions, long before you risk a crew. That data then feeds into the design of future fusion ships, nuclear designs, or whatever crude propulsion we end up using. The first era of interstellar exploration is almost certainly robotic, with beamed sails and maybe fusion probes racing ahead, and humans following much later, using information gathered by machines. But there's one more level above fusion and laser sails that people always bring up, the really extreme ideas. antimatter engines, and even warp-like concepts, things that promise insane performance but are way beyond engineering today. So once you've pushed photons and fusion as far as they go, what happens when you start asking whether the ultimate fuels or even space-time itself can be turned into an engine for crossing the stars? If fusion and giant lasers still feel limited, you might ask a dangerous question. What happens if you use the most efficient engine nature allows, turning mass directly into energy? That's what antimatter offers on paper. When a particle of normal matter meets its antimatter twin, both are completely converted into energy, following the famous energy equals mass times the speed of light squared. The result is brutal. 1 kilogram of antimatter reacting with 1 kilogram of normal matter releases on the order of 9 times 10 to the 16 joules. In plain language, that's roughly the same energy as a 43 megaton nuclear explosion, about the size of the largest bomb humans have ever tested. For interstellar propulsion, that is top-tier energy density. Nothing in chemical or normal nuclear reactions comes close. With that kind of punch, in theory, you can design engines that reach a big fraction of light speed with far less fuel mass than fusion would need. So if antimatter looks like the ultimate rocket fuel on paper, what's actually stopping you from building an antimatter-powered starship? The first hard stop is production. Right now, all the antimatter produced on Earth each year in all labs combined is measured in nanograms, billionths of a kilogram. We make it in particle accelerators by slamming high-energy particles together and catching the rare antimatter fragments in magnetic traps. That process is extremely inefficient. The energy cost per gram is enormous, and if you tried to scale it up, you'd be talking about effective costs in the trillions of dollars per gram. For a starship, even a very efficient one, you're not talking about grams. You're talking about kilograms or tons of antimatter. In today's terms, that's like trying to fill a swimming pool using 1 raindrop per day and then calling it a construction timeline. The order of magnitude gap between what we can make and what we would need is extreme. Even if you hand-wave the production problem and pretend you somehow have tanks of antimatter ready to go, the next problem is worse: storing it without dying. Antimatter cannot touch normal matter, ever, because the moment it does, it annihilates and dumps all that stored energy. So you can't just put it in a metal tank. You have to suspend antimatter particles in magnetic or electric fields inside ultra-high vacuum with no contacts to the walls. We know how to do this in small traps on Earth, but we're talking about tiny amounts, stored for short times in heavily controlled lab conditions. A starship would need to hold much larger amounts in a dynamic, vibrating, accelerating vehicle for years or decades, while being hit by cosmic rays, micrometeoroids, and constant mechanical stress. A single failure in containment is not just a leak, it's a catastrophic event. If a chunk of antimatter hits the wall, it can release enough energy locally to damage the containment system, which causes more antimatter to escape, and so on. In the worst case, your propulsion system becomes its own bomb. Engineering a storage system that can survive every possible failure mode with 0 critical failures over century-scale missions is orders of magnitude beyond anything we've built. It's hard enough to keep cryogenic fuels from boiling off over months. Keeping antimatter perfectly bottled for decades is another level. Now, because antimatter sounds extreme, people often jump one step further and ask about going around the speed limit itself, using warp drives, wormholes, and other exotic tricks. So where do those actually stand? General relativity, our best theory of gravity and space-time, does allow some weird solutions if you write down the equations in very clever ways. You can get mathematical models of warp bubbles, like the Alcubierre drive, where space itself compresses in front of a ship and expands behind it, letting you effectively move faster than light without locally breaking the speed of light rule. You can also find conditions that describe traversable wormholes, tunnels through space-time that could in theory connect distant points. The catch is that these solutions require things we have never observed and don't know how to create, like regions of negative energy density or exotic matter with properties that no real material has. They also tend to need absurd energy densities, sometimes comparable to the total energy output of stars or even galaxies, focused in strange shapes. Right now, these ideas sit in the same category as perfect perpetual motion machines, fun to explore mathematically, useful to map what the laws of physics do and don't strictly forbid, but not engineering designs. There's no lab-scale warp bubble. There's no tiny wormhole experiment you can point to and say, we've started. They're interesting edge cases in our equations, not technologies. So when people ask, could antimatter drives or warp engines bring interstellar travel into our near future? What can you honestly say? The straight answer is that they don't help you set a date yet. Asking when humans will achieve interstellar travel using antimatter or warp tech is like asking what year we'll launch the first starship powered by a fantasy element we haven't discovered. Until you can store macroscopic amounts of antimatter safely for long periods, antimatter drives stay on the whiteboard. Until you have at least small, controlled demonstrations of space-time manipulation that go beyond normal gravity, warp and wormholes stay in the category of interesting but speculative. They stretch the upper bound of what might be eventually possible in a far future, maybe thousands of years from now, but they give you almost no information about the realistic first wave of interstellar missions. So you have a spectrum, from chemical rockets to nuclear to fusion to beam sails to antimatter and exotic space-time tricks. As you move along that line, the theoretical performance gets better, but the technology gets more speculative and distant. The early, real interstellar missions are almost certainly going to sit in the region where physics is solid, and engineering, while hard, is at least in reach. Things like fusion, advanced nuclear concepts, and beamed propulsion. Antimatter and warp drives are more like the long tail, the maybe one day end of the chart. Now, here's the twist though. Even if you had a perfect engine tomorrow, something that could push a ship to 0.2 C without burning tons of fuel, you still hit another hard ceiling, the one you carry in your own cells. Because fantasy engines don't protect you from radiation, muscle loss, bone damage, and all the biological wear that comes with years in deep space. So after you push the physics as far as it will go, the next brutal question is, how does the human body itself handle deep time between the stars? You can build a perfect engine on paper. You can solve the rocket equation and even find a way around hauling fuel. But if the crew falls apart halfway through the trip, the mission still fails. The next wall is ugly and simple. Your body is built for Earth, not for decades in deep space. Start with radiation, because that one doesn't care how tough you think you are. Inside Earth's magnetosphere, you're shielded from most of the charged particles flying around the galaxy. Step outside that bubble, and you're in a constant storm of galactic cosmic rays and solar particles. Even a short Mars mission, 1 to 2 years round trip at today's speeds, is already close to current career limits for astronaut radiation exposure. The numbers are high enough that mission planners worry about long-term cancer risk and damage to the nervous system. And that's for a mission that still spends a lot of time within partial protection from the sun's magnetic field. Now, stretch that out to a decades-long interstellar mission, even at 0.1 C. You're talking about spending 10, 20, maybe 40 years in an environment where high-energy particles are constantly punching through your body, breaking DNA, creating mutations, and slowly increasing your odds of cancer, cardiovascular problems, and other radiation-linked diseases. Electronics get hit too. Bit flips in memory, sensor degradation, slow damage to solar cells and circuits. You can't just hand-wave that away. You need shielding, and not just a thin film of metal. We're talking meters of water, or thick layers of plastic rich in hydrogen, like polyethylene, or even big magnetic fields to bend charged particles away from living spaces and sensitive hardware. All of that adds mass, a lot of it. Tons and tons of water or shielding material, or heavy coils for magnetic protection, and every extra ton is something your engine has to accelerate. So that pushes you right back into the energy and propulsion problems you were trying to solve. So when you hear interstellar crewed mission, you should quietly add plus a mobile radiation bunker that can survive decades in deep space to that sentence. Even if you beat radiation with enough shielding, there's another slow killer waiting for you: microgravity. Your bones and muscles assume one constant condition, roughly 1 G, on Earth's surface. Take that away, and your body starts to adapt, in the wrong direction for long-term health. In orbit, astronauts can lose around 1 to 2% of their bone mass per month, and they see serious muscle atrophy, especially in the legs and back. That's with intense exercise routines every day on missions that last months, not decades. If you extend that environment to years without a good fix, people come back essentially weakened, more fragile, and at risk for fractures and long-term issues. On a multi-year interstellar trip, if you just let everyone float weightless, the damage becomes catastrophic. You'd arrive at another star with a crew that can barely walk, with compromised bone structure, heart changes, and all the second-order medical problems that come with a body that's been detrained by microgravity for half a lifetime. The only serious way out is artificial gravity. The straightforward approach is to spin at least part of the ship so that centripetal force pushes people toward the outer rim like gravity. To get close to 1G without making people dizzy or sick, you need a habitat rotating with a radius of tens to hundreds of meters, spinning at a carefully chosen rate. That's not a small D-tweak. You're now talking about big rotating structures, bearings or tethers, structural arms, and a ship that has to hold its shape under both rotation and whatever small accelerations your engine produces. At relativistic speeds, any imbalance is dangerous. So your simple starship starts to look like a hybrid of a space station and a fast interstellar vehicle with complex moving parts that have to last for decades without serious failure. Then there's life support. You can't just load a warehouse of food and oxygen and call it a day. For a mission that lasts 20 or 40 years, and definitely for anything longer, you can't pack every kilogram of water, oxygen, and food as cargo. The mass would be ridiculous. Instead, you need closed-loop life support, systems that recycle more than 90 to 95% of your air and water and produce food on board. That means systems to scrub carbon dioxide and turn it back into oxygen, to reclaim water from breath, urine, sweat, and other waste, and to grow edible biomass using hydroponics, aeroponics, or bioreactors. On the International Space Station, we already do part of this. A large fraction of water is recycled, and some air is regenerated, but food still comes up from Earth in cargo ships, and the system is not fully closed. Unexpected chemistry has caused issues in the past. Microbes behave differently in microgravity, and hardware wears out. Scaling that to a fully closed ecology that runs for decades without resupply is a project on its own. You probably need years of testing in Earth orbit, on the Moon, or on Mars bases before you would trust such a system on a one-way, no-resupply interstellar mission. All of that assumes human lifespans roughly like today, where people live into their 80s or 90s. But what if you change that variable? Is there any way biology itself could stretch to meet interstellar timescales? If medicine pushes healthy human lifespans out to 120 or 150 years, suddenly a 40 to 60 year round trip to a nearby star doesn't sound completely insane. A person could train, launch in midlife, spend decades in transit, work at the destination, and still have time left. The other path is more dramatic. Some kind of safe, reversible suspended animation or deep stasis. If you can slow biological processes way down without destroying the brain and body, an 80-year trip could feel like going to sleep and waking up in a different star system. Right now, cryopreservation and similar techniques work on certain cells, organs, and some small animals, but not on complex primate brains or whole humans. The problems include ice crystal formation, toxicity from cryoprotectant chemicals, and damage during cooling and warming. Even if we invent better methods, proving that a human can go into stasis, stay there for decades, and come back out with their mind and health intact is an enormous ethical and technical challenge. Realistically, we're probably at least a century away from even thinking about trial-scale human stasis experiments, and that's if research and regulation move fast. If you can't stretch an individual's lifespan enough, and you don't trust stasis, there's one fallback option that keeps showing up. You don't send a crew, you send a society. That's the generational ship idea. You launch not a small team, but a whole community. The children who grow up on board take over from the original crew, and their children might be the ones who finally arrive. You can spread the mission over centuries by accepting that no one who leaves the solar system will ever see the destination. But that throws you into a completely different category of problem. You're not just managing hardware failure and radiation anymore, you're managing culture. A generation ship has to keep a stable, functioning social structure for hundreds of years in a closed environment. You need reliable education so knowledge doesn't decay. You need governance and conflict resolution that can handle stress, boredom, without collapsing. You have to manage population size, resources, and psychological health over many generations with no outside reset button. Biology here is not just DNA and cells, it's human behavior, relationships, ideologies, and the way groups evolve over time. And that is arguably harder to engineer than a fusion reactor. So even if physics lets you go fast, and engineering gives you engines that can push a ship to point 1C or beyond, the human body and human society still impose hard constraints. Radiation, microgravity, closed ecosystems, lifespan, psychology, all of that feeds back into the core question: when will humans really travel to another star? Because whatever date you pick has to be late enough that we've not only mastered the engines, but also these deep, slow biological and social challenges. And if you accept that multi-decade trips and multi-generation missions might be necessary, the next step is obvious. You stop thinking of ships as vehicles with cabins and start thinking of them as moving worlds, huge habitats where people live entire lives in transit. So what does that look like when you scale it up? How big does a self-sustaining world between the stars have to be before it's actually stable? How big does a ship have to be before it stops being a vehicle and starts being a place where whole generations can live and die? When you run the numbers, a real generation ship looks a lot less like a rocket and a lot more like a small, engineered world. To keep a human population stable for centuries, you don't just send a handful of people. You want a few thousand at least, to keep genetic diversity healthy and to cover all the skills a complex society needs. Engineers, doctors, farmers, teachers, mechanics, scientists, caregivers, everyone. That many people need space, not just bunks. You're talking about tens of cubic kilometers of pressurized volume, not a narrow tube. Enough room for living areas, workplaces, storage, and wide agricultural zones. For food alone, you're looking at farm areas on the scale of square kilometers, layers of hydroponic racks or stacked greenhouses. When you put all that mass together, structure, shielding, soil or nutrient systems, machinery, water, air, you're easily in the range of millions to billions of tons. That's the mass of a small asteroid reshaped and hollowed out, not a sleek starship in the sci-fi sense. So if that's the scale of a genuine world ship, the next question is, how long does it actually cruise between stars if it never gets anywhere near light speed? Say your big habitat travels at about 1% of light speed. That's roughly 3,000 kilometers per second, about 6.7 million miles per hour. On paper, that is far slower than the 10 or 20% of light speed you might squeeze out of fusion or beamed probes, but it's still orders of magnitude faster than Voyager. At that speed, crossing the roughly 4.24 light-years to Proxima Centauri takes around 424 years in the external frame. That's maybe 15 to 20 human generations. For the people on board, the mission isn't a single dramatic expedition. It's normal life. Kids are born, grow up, work, have their own kids, grow old, and die, all while the world outside is just a star field slowly changing over centuries. Daily life becomes civilization in transit, not crew on a mission. Once you accept that timescale, another problem shows up: keeping the environment stable for that long. And this isn't just about air filters and water tanks, it's about a full artificial biosphere. On Earth, nature handles oxygen cycles, nitrogen cycles, soil health, pollination, and microbial balance through huge, complex ecosystems. On a world ship, you have to engineer that from scratch and keep it stable for hundreds of years. You need plants to take in carbon dioxide and release oxygen. You need systems to process waste into nutrients. You need controls on pests, fungi, and bacteria so they don't overrun the system or collapse it. Small testbeds on Earth, like closed ecological experiments, have struggled to stay balanced even for a couple of years. Hidden chemistry, unexpected microbial effects, and tiny leaks can cause big shifts in oxygen levels and other key variables. Stretch that to centuries, and you're in a very hard regime. You need sensors everywhere, automation that can respond when something starts drifting, and human crews trained to understand and manage complex ecology, not just plumbing. It's not just about building a working system once, it's about making one that can be repaired, upgraded, and adapted by people who weren't even born when the ship launched. And even if the air and food stay stable, you still have one more layer that can break the whole thing: the people. What stops a world-sized ship from tearing itself apart socially long before it reaches another star? Over a few centuries, you can almost guarantee conflict, changing beliefs, and power struggles. You're putting thousands of humans into a closed environment with limited resources and no way to move somewhere else if they don't like how things are run. That's a pressure cooker for psychology. You might need formal governance systems that are designed with long-term stability as a core goal, not just short-term efficiency. You may lean on AI systems to mediate disputes, track resource use, and warn when social tensions are rising. Some people even suggest deliberately engineering culture, values, and education so that patience, cooperation, and long-view thinking are built in from childhood. The success of a generation ship depends as much on these soft systems as on engines and radiation shielding. A reactor can be repaired by swapping out parts. A social collapse can't be patched that easily. You'd have to think about laws, traditions, conflict resolution methods, and mental health support as core parts of the ship's design. Looking at those demands, from mass to ecology to culture, you hit a final question. When in history does a civilization even try something this huge? A true world ship is an enormous capital project. Before humanity attempts to build one, you'd expect a long ladder of earlier steps. Permanent colonies on the moon and Mars, not just outposts, but real towns. Large orbital habitats in the style of O'Neill cylinders, rotating structures kilometers long housing tens of thousands of people in Earth orbit or around other planets. Industrial operations throughout the asteroid belt, mining rock and metal and ice, and using them to build big structures in space. By the time a world ship is on the table, grabbing an asteroid and turning it into a city-sized habitat should be routine work. That level of infrastructure is not a 21st century thing, or even a simple next century step. You're talking about a multi-century buildup of space industry and space society. That's why most serious discussions place generation ships and world ships not at the start of the interstellar era, but later, after uncrewed probes and maybe smaller, faster crewed missions have already opened the way. World ships are a picture of a mature interstellar civilization, one that doesn't just visit other stars, but migrates between them with whole communities. So you end up with two very different tracks: fast, risky missions with small crews and extreme tech, and slow, massive world ships carrying whole societies. Both point to the same thing. The first step between stars is probably not a family in a sleek ship. It's either robots or a city. And that raises the next hard question. Before you ever risk building a world ship or sticking people on a fusion sled to another star, who actually goes first? Who scouts the way, maps the targets, and builds the first footholds so humans don't arrive blind? Why would you gamble human lives on the very first trip to another star when you can send something that doesn't breathe, doesn't sleep, and never complains about a one-way ticket? This is why robots go first. Machines don't need air, gravity, or food. They don't care if the cabin temperature drops a few degrees. They can tolerate accelerations that would kill you in a fraction of a second, and radiation levels that would send your cancer risks through the roof. You don't need showers, you don't need bedrooms, you don't need a doctor on board. You just need power, shielding for electronics, and a working antenna. That means the first true interstellar missions are almost certainly uncrewed probes, not heroic crews and shiny ships. Think Starshot-style sail probes weighing a few grams boosted to 0.2 C, or heavier nuclear and fusion scouts creeping along at 0.01 to 0.1 C. The risk profile is completely different. If a probe fails, you lose hardware and science time, not human lives. For a civilization that's just testing the waters beyond the solar system, that trade is obvious. But if no one is on board, making decisions moment by moment, who actually runs the mission once the probe leaves home and vanishes into the dark? That's where AI stops being a buzzword and starts standing in for a crew. As AI systems become more capable, you can treat your probe as an autonomous explorer, not just a remote-controlled camera. It navigates around dust and debris. It decides when to rotate and point its instruments. It compresses and prioritizes data before sending it back. In more advanced concepts, the AI doesn't just explore, it builds. Picture a probe arriving at a nearby system like Proxima Centauri, using magnetic or fusion-based braking over decades to slow down, then spending another few decades mining local asteroids or moons with onboard robots. It could assemble communication relays in orbit, lay out fuel depots, or even erect small robotic factories and habitats on suitable bodies. By the time humans ever show up, there's already infrastructure waiting for them, built by an AI crew that never needed sleep, food, or a return ticket. That sounds powerful, but there's an immediate problem. How do you run a mission like that when every question you ask takes years to get an answer? At 4.24 light-years away, the distance to Proxima Centauri, a radio or laser signal moving at light speed needs at least 4.24 years to get from the ship to Earth. If you send a command back, that's another 4.24 years. So a basic "hey, should I do this?" followed by "yes, go ahead" takes roughly 8.5 years round trip. That makes real-time control impossible. You can't joystick an interstellar probe the way you maneuver a Mars rover with a few minutes of delay. Your probe's AI has to be genuinely autonomous in critical ways. It needs to handle navigation without waiting for permission, handle hazard avoidance, choose targets for closer study, and react to unexpected events, all locally. It also has to be robust. Software bugs that only show up after 20 years of operation are not theoretical anymore. They're a mission-ending risk. Memory errors from radiation, sensor degradation, and hardware failures all have to be anticipated. That means layered fault tolerance, redundant systems, and AIs that can diagnose their own problems and switch to backups without panicking. You can still update software slowly over that 4+ year delay, but you can't rely on constant human oversight. For the first interstellar missions, autonomous enough not to need you most of the time is a hard requirement. If you can't steer it live and you can't fix every problem it hits, what exactly are you hoping this lonely robot brings back that justifies decades of effort? The answer is simple. Data is the real payload. Early interstellar probes won't be delivering samples or bringing back rocks. They'll be sending raw information, terabytes of it, over narrow, carefully aimed communication beams. You'll get high-resolution spectra of exoplanet atmospheres showing what gases are present, whether there's oxygen, methane, carbon dioxide, water vapor. Combinations like oxygen and methane, far from equilibrium, could be signs of biological activity. You'll get detailed imaging of planets, moons, rings, and asteroid belts in those systems, far beyond what telescopes around Earth can resolve. You'll map magnetic fields, particle environments, and dust densities, all of which matter for future ships that have to travel and maneuver there. You need that level of detail before you even think about sending humans. You want to know if a planet has a thick atmosphere or a vacuum, if it's bathed in flares, if its radiation belts are lethal, if there are stable orbits for stations or stations plus moons combinations you can exploit. And you probably won't get all that from one probe. You'll send multiple waves, different designs, different instruments, some flying through, some breaking into orbit, building up a multi-century catalog of hard data about your target stars. Only once your models are anchored by that does it make sense to discuss putting people on a ship and pointing them at one of those worlds. So that circles back to the schedule question. If robots clearly go first, when do these first interstellar scouts actually leave? And how many waves come before a human even has a shot? Given current trends, slow, uncrewed interstellar probes cruising at speeds like 0.01 c or less are plausible sometime in the 22nd century. Those might be nuclear electric or advanced fission fusion vehicles still taking hundreds of years to arrive, but acting as proof of concept and long-term testbeds. As fusion, materials, and beamed propulsion mature, higher speed probes in the zero point 0.1 to zero point 0.2 C range could follow in the 22nd or 23rd century if civilization keeps advancing and stays stable enough to fund them. By the time you consider a crewed interstellar mission, you're probably looking at a sky where multiple nearby stars already have robotic probes there or en route, and decades of data streaming back. That's the only sane way to do it. You don't throw humans into a completely unknown system on the first try. You let robots map the minefield first, locate the safe or promising zones, and maybe even build the first pieces of infrastructure humans will rely on when they arrive. So the pattern starts to emerge. Robots first, humans later. And the gap between those two depends on how fast your technology and your civilization grow. Which leads to the next hard filter on your timeline. Even if you have designs for probes, sails, and ships, when does your civilization actually have enough power, money, and industrial muscle to treat interstellar missions as doable projects instead of science fiction posters? At some point, you have to stop asking, can we design a starship? And start asking, can our entire civilization afford to run one? That's where the energy scale hits you, because interstellar travel isn't just a tech problem, it's a civilization-level budget problem. One way to think about that is the Kardashev scale. It classifies civilizations by how much power they can handle. Type 1 uses roughly all the energy available on its home planet. Type 2 taps into most of its stars' output. Type 3 goes up to a whole galaxy. Right now, humanity sits around 0.7 on that scale. We're using a few times 10 to the 13th watts of power, tens of terawatts, across the entire planet. That's everything. All power plants, all solar, all industry, all cities. Interstellar missions, especially fast crewed ones, start to look like Type 1 Plus or even early Type 2 projects. They're not in the same class as build another rocket launch site. They're in the class of reroute a noticeable chunk of your species' power output for decades. So let's put that into a concrete number. Earlier, we talked about a 1,000-ton ship, 1 million kilograms, cruising at 10% of light speed. The kinetic energy for that kind of speed is on the order of 4.5 times 10 to the 20th joules. Now, spread that energy over 10 years of buildup and acceleration. 10 years is about 300 million seconds. Divide the energy by that time and you get an average power of around 1.5 trillion watts, roughly 1.4 terawatts. That's close to 10% of all the power humanity uses today, dedicated to a single mission. And that's assuming perfect efficiency. Real systems are not perfect. You lose energy to waste heat, to beam spread, to conversion losses, to construction and support infrastructure. When you factor that in, the real requirement balloons. You're realistically talking about a civilization that can produce hundreds of terawatts, maybe even into the petawatt regime, where 1 petawatt is 1,000 terawatts. At that level, a starship isn't just a spacecraft, it's a power project. You're building something that during its acceleration phase pulls as much power as a large region or a whole planet currently uses. To reach that kind of output, you don't just add a few more coal plants or solar farms. You need a different energy architecture altogether. Part of that will be solar, but not just panels on rooftops. You'd be looking at space-based solar arrays in high orbits, above cloud cover and night, spanning square kilometers, beaming power down or across space. On top of that, you almost certainly need mature commercial fusion power, reactors that can run reliably for years with high output and low risk on Earth and in orbit. In the extreme, you might start building what's sometimes called a Dyson swarm. Not a solid shell, but a huge constellation of solar collectors scattered around the sun, each harvesting a slice of its output. This isn't just about bigger plants, it's about restructuring how your whole civilization uses and moves energy. Grid-level storage, power beaming, orbital infrastructure, industrial capacity to build massive arrays in space and maintain them. That kind of architecture takes decades to stand up, even if your tech is good. You're effectively saying, before we fly to another star, we have to build a power system that treats the sun as our main generator, not just our background light. Then there's the money side of can we afford this, on top of the raw watts. Look at Apollo as a benchmark. At its peak, the Apollo program ate about 4% of US GDP. It was a huge national focus, industrial mobilization, and intense public attention, and it lasted for a finite period. A first crewed interstellar mission will dwarf Apollo in complexity and cost. You might be committing a similar fraction of total global economic output not just for a few years, but for decades to develop propulsion, build infrastructure, launch test missions, and then finally send the crewed mission itself. Or alternatively, you imagine a future civilization that is far richer, spread across multiple planets and orbital habitats, where committing that much energy and money is the equivalent of a major infrastructure project, not an all-in national race. Either way, you need more than just technology. You need a stable, cooperative, global, or multi-planetary economy that can support multi-decade mega-projects without collapsing or losing interest halfway. All of this loops back into the timeline in a very direct way. Until your total power output climbs by at least 1 to 2 orders of magnitude beyond today, fast crewed interstellar missions aren't just technically hard, they're economically and energetically out of reach. If you keep using only tens of terawatts as a species, dedicating a significant fraction of that to a single mission is unrealistic. When your total capacity hits hundreds of terawatts or into the petawatt regime, suddenly the numbers start to look less insane. A 1.4 terawatt acceleration phase becomes a few percent of your total output, instead of 10 or more. Building huge laser arrays, fusion arrays, and orbital infrastructure becomes just another line item in a very large budget. That's why when you try to put a lower bound on when will humans achieve interstellar travel, you can't just look at engine tech or medical advances. You have to look at how fast human energy production is growing, how quickly fusion comes online, whether we actually build large-scale solar-based power, and whether our civilization remains stable enough to do long-term planning at that scale. Realistically, that pushes you out of this century and probably out of the next. Hitting the 100 terawatt to petawatt band feels like 22nd to 23rd century at best, and that's under optimistic assumptions. So even if you have the will and the physics and the basic designs, interstellar travel is gated by when your civilization hits the right power level and economic stability to take it on without breaking itself. And once you're in that energy-rich future, another question appears. If you can finally afford starships, where do you actually go first? And how do you aim at a moving target that's light years away in shifting position the whole time? Once you finally accept that starflight is possible, but hard, the next question is very blunt. Where do you actually go first, and how do you hit a moving target that's light years away without missing by a ridiculous distance? The obvious first stop is the Alpha Centauri system, because it's the closest neighborhood you have. There are 3 main stars there: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Proxima is the small red dwarf hanging a bit off to the side, about 4.24 light-years from us. We already know it hosts at least one planet, Proxima B, roughly Earth mass, sitting in the so-called habitable zone where liquid water could exist on the surface. On paper, that sounds like a dream target. Near a star, Earth-sized planet, right distance from the star. The problem is that Proxima is a flare star. It can blast the planet with intense bursts of radiation, ultraviolet and X-rays that might strip atmospheres or fry surface life. So habitability is uncertain at best. Alpha Centauri A and B, which are more Sun-like, probably have planets of their own, and some candidates have been reported, but not all are confirmed yet. So even in the closest system, you still have work to do just to know which world is worth aiming at. And if the nearest star system is already this messy, how do you even build a target list for everything within, say, 10 or 20 light years? That's where the exoplanet census comes in. Over the last couple of decades, missions like Kepler and TESS have confirmed thousands of planets around other stars, and telescopes like the James Webb Space Telescope and large ground-based observatories are starting to study their atmospheres. For interstellar missions, you're not just looking for any planet. You want a specific profile. You want stars that are stable and long-lived, not blasting out constant flares or about to swell into giants. You want planets in the right temperature range, with orbits that keep them in a zone where liquid water is possible over long times. And if you can, you want hints in their atmospheres, gases like oxygen, methane, carbon dioxide, and others in combinations that suggest active chemistry or even life. As the surveys improve, the short list of targets will sharpen. Instead of saying nearest star, you'll say nearest star with a stable K-type or G-type star, a rocky world in the habitable zone, and an atmosphere that looks promising. That list might be only a few systems within 20 light years. Those become your high-priority destinations, the places where it actually makes sense to send multi-decade probes or worldships instead of just doing flybys. But picking the star is only half the problem. All those stars are moving, and they don't sit still while you're in transit. So how do you steer a ship over decades and still arrive where you meant to? Every star in the sky has its own proper motion, a slow drift across the background as it orbits the center of the galaxy. Over tens of thousands of years, that adds up to big changes in position. Even in a 50-year journey, a small error in your initial direction can turn into a miss that's billions of kilometers off. This isn't like aiming at a fixed island across an ocean. It's like firing a bullet at another bullet while both are moving on curved paths around a third object. To navigate that, you need extremely precise measurements of stellar positions and motions, down to milli-arcseconds, tiny angles. Space missions like Gaia are building catalogs like that now, but for starships, you'll want even better. On board, the ship will constantly refine its trajectory, using very stable beacons like distant quasars, pulsars, and a detailed map of nearby stars. The navigation system has to work for decades, maybe with minimal help from Earth because of the light speed delay. Tiny course corrections made early in the mission prevent huge errors later. Navigation becomes a continuous task, not a set-it-and-forget-it event at launch. And even if you get the pointing perfect and hit the system on target, there's another hard step: stopping. Getting to 0.1 or 0.2 times light speed is only half the story. How do you slow down without overshooting the entire system? Deceleration is a major design choice. One option is to carry extra propellant specifically for braking, which means a bigger, heavier ship and more energy to accelerate in the first place. Another approach is to use the environment. A magnetic sail is one idea, a huge loop or structure that interacts with charged particles in the interstellar medium. As the ship plows through the thin gas between stars, the magnetic field pushes against it and slowly bleeds off speed. You can also use a light sail, not just for acceleration, but for braking. Near the target star, you can angle the sail so that the starlight pushes against your motion. In more advanced concepts, a second laser array placed in the target system could fire at your sail in reverse, acting as a brake beam. Each of these choices hits the design in different ways. Carrying extra propellant adds mass. Magnetic sails add large structures and complexity. Relying on a pre-positioned laser means you have to send smaller probes ahead of time to build that array. Deceleration strategy isn't a small detail. It locks in what kind of propulsion you use, how heavy the ship is, and how long the mission takes. And all of that loops back into, when is this even feasible? Because heavier ships and more infrastructure means you need a more advanced civilization before you can seriously attempt it. Now, tie this back to motivation. If all of this is so complex, what could actually push humanity to commit to a first crewed mission earlier than pure tech forecasts would suggest? The answer is target quality. Right now, we know a few interesting planets, but nothing that screams, this is definitely alive. If in the next century or two, telescopes find a nearby system, say within 3 or 4 light years, with a planet that clearly shows strong biosignature gases in its atmosphere, for example, a stable mix of oxygen and methane, maybe plus other indicators that really point towards life, that one discovery turns interstellar travel from long-term dream into urgent priority. Public interest, will, and economic backing all spike. Instead of asking, why spend so much to go, the argument becomes, how can we not? That kind of discovery could pull the launch date forward by decades, maybe even a century, compared to a timeline where you never find a clear, life-bearing world next door. So, picking where to go, understanding how it moves, figuring out how to slow down, and waiting for the right kind of planet to show itself all feed into the real question under all of this. When does the first human ship actually leave? You've seen the constraints, the tech, the biology, the energy, the targets. Now the next step is to pull it all together and ask not for a single date, but for a realistic range of centuries where a first human interstellar mission actually fits. You've got all the pieces on the table now, but they don't line up to a single year. They line up to a spread of futures, some where we get there soon on cosmic timescales, and some where we never go at all. Start with the slow, cautious path. In a conservative scenario, fusion power keeps slipping, big space projects get delayed. You get progress, but it's stop-start, with long gaps. In that world, the first real interstellar hardware is uncrewed and slow. Maybe sometime in the 22nd or 23rd century, you launch probes that cruise at about 1% of light speed, around 3,000 kilometers per second, about 6.7 million miles per hour. That is fast compared to Voyager, but still hundreds of years to the nearest star. These missions are mainly science and tech demos, not serious precursors for humans. Later, as fusion, materials, and energy infrastructure finally harden, you push up to 10% of light speed with more advanced probes, maybe in the 23rd or 24th century. Now travel times to Proxima or Alpha Centauri go up into the few-decade range. You start getting high-quality data from other systems within a human lifetime of launch. But all of this is still robotic. In this conservative track, a first crewed interstellar mission doesn't leave before the 24th or even the 25th century. When it does, it's probably not sleek and fast. It's either a slow generational world ship or a heavily shielded fusion craft on a mission that takes decades. Life support has to be rock solid. Social systems have to be tested on big orbital habitats first. And no one pretends this is a quick hop. Now, flip to a more aggressive but still realistic future. If things go right, what does fast actually look like without invoking magic? In an optimistic scenario, fusion hits practical maturity late in the 21st century. That means actual commercial fusion plants feeding grids on Earth and eventually power systems in space. At the same time, reusable launch vehicles and in-space construction take off. So by the 22nd century, you're building big orbital stations and solar power platforms. Global or multi-planetary industry starts to spread beyond Earth, mining asteroids, assembling huge structures in orbit. On top of that, governments and private groups treat beamed sail infrastructure, giant laser arrays or microwave arrays, as a flagship global project, like a combination of the internet, GPS, and Apollo in one. If all that lines up, you could see robotic probes at 10 to 20% of light speed launching in the late 21st or early 22nd century, not just theory, but actual missions to Proxima, Alpha Centauri, and other nearby targets. Those probes arrive in 20 to 40 years, send back torrents of data, and prove your propulsion concepts in the real interstellar environment. With that experience, plus a massive energy base and decades of learning from closed habitats on the Moon, Mars, and in orbit, a first high-speed crewed mission becomes plausible in the 23rd century. That's the best reasonable case path. No new physics, just a long chain of successful engineering and social choices. There's also a darker timeline you have to acknowledge, where the bottleneck isn't physics or engineering, it's history. In a stagnation scenario, humanity keeps getting hit by crises, climate shocks, wars, pandemics, resource collapses. Space budgets stay small, focused on near-Earth applications, communication, weather, maybe some Mars or Moon science. We still send robotic probes to the outer planets, maybe to the Kuiper Belt, maybe one or two very slow craft toward the Oort cloud, but the step from outer solar system to interstellar never gets funded or keeps getting postponed. The tech to do it remains within reach, but the will and stability never line up. On that track, human interstellar travel is pushed back by centuries or millennia, or simply never happens. Physics allows it, but culture and economics don't. In that sense, never is a real option, not because the speed of light is too harsh, but because a species that can't keep its own house in order for a few centuries doesn't get to run multi-century starship projects. Then there's the wild card, the scenario people love to hope for but you cannot plan around, the physics surprise. There is a small but non-zero chance that future physics gives you a new kind of engine or energy source, something we don't have on the table right now. Maybe a way to tap vacuum energy efficiently, maybe a new kind of fusion we can ignite easily, maybe some controlled space-time effect that acts like a mild warp or drag reduction on interstellar scales. Right now, that's speculation, not engineering. You can't write a schedule that says, in 2085 we will discover new physics, but if such a breakthrough arrived, it could compress timelines hard. Instead of waiting for late 23rd century infrastructure, you might see serious crewed mission plans in the mid-22nd century. That's the "we got lucky" branch. Exciting to think about, dangerous to rely on. So when you step back from all of this and you're forced to give one honest answer to when will humans achieve interstellar travel, what can you actually say without hand-waving? You can say this: not this century. There is simply too much to build, from fusion and beamed power to closed life support to radiation shielding to massive energy infrastructure. None of that is the interstellar age yet. It's the prequel. It's the steam engine era before railroads and jets, the clunky early stage where the key pieces show up separately long before anyone bolts them together into a starship. The rockets we test, the habitats we build, the power systems we refine, the way we manage global cooperation on big projects, all of that is laying down the base layer for people who will live in the 2200s, 2300s, and beyond. When they build starships, a lot of their standard tech will trace back to what you're watching get invented now. If the hardware we're building is set up, then what about the knowledge we're collecting? How much does that really matter for a mission that flies in the 23rd or 24th century? Every spectrum of an exoplanet's atmosphere you see in a press release, every new entry in a stellar catalog, every radiation reading from a probe beyond Earth's magnetosphere is raw input for somebody's future mission design. When an interstellar ship crew sits down to plan their route and pick their destination, they're going to open databases built from telescopes like Kepler, TESS, JWST, giant ground-based observatories, and whatever comes after. Our current measurements of how cosmic rays behave past the orbit of Jupiter, how dust is distributed in the outer solar system, how flares from red dwarfs actually look over time, all of that will feed into their risk models, their shielding calculations, and their navigation plans. By the time a human ever straps into a seat on a ship aimed at another star, the maps, the hazard charts, the target shortlists, and even the basic physics models for their engines will be built from data gathered in your era and the ones right after. What JWST saw in that atmosphere is not just a news headline, it's the reason some mission planner in the future checks one system off and circles another in red. But there's another effect that hits much closer to home. Once you really internalize interstellar distances and times, it changes how you look at Earth itself. When you accept that even light needs 4.24 years to get from here to Proxima Centauri, Earth stops feeling like a generic place in space and starts feeling like a tiny, hard-won safe zone. One astronomical unit, about 150 million kilometers or 93 million miles from our star, is the thickness of the cozy shell we live in. Beyond that, the desert stretches for thousands of astronomical units before you even leave the sun's influence, and then the distances jump to light years. There is no next Earth over you can just drive to if you wreck this one. Thinking seriously about starflight forces you to think seriously about long-term survival. You need stable energy systems that don't burn your environment down. You need a civilization that can plan in centuries, not just election cycles. You need a planet that stays habitable long enough to build all the infrastructure we talked about. Interstellar thinking makes planetary stewardship less abstract. If you want your species to reach another star, you have to keep this world functional long enough to finish the job. There's also a mental breakpoint out there in the future, a psychological line that once crossed splits human history into before and after in a very sharp way. At some point, a person is going to wake up, strap in, and feel constant acceleration under their feet in a ship that's on its way to zero point 0.1 C or more, with a destination star in the flight plan that is not the sun. That moment is a kind of singular event for our story as a species. Everything before that is planetary history. Everything after that is interstellar history. The first time a human looks out at a nearby star and knows that's where I'm going, not back home, the psychological cage that says we are bound to this one star forever breaks. On the scale of human development, that shift could be as big as the invention of agriculture, writing, or powered flight. It doesn't suddenly solve all our problems, but it permanently changes what we consider possible. Kids born after that launch will grow up in a world where people go to other stars is not a fantasy line. It's a historical fact. Their baseline expectations for the future will be completely different from yours. So, where do you personally fit into a story that stretches across centuries like that, if you'll never sit in that starship seat yourself? You're part of the setup crew, whether you like it or not. The engineers pushing on fusion reactors, on high-efficiency solar, on better batteries and grids, they're solving the energy side of the problem. The scientists mapping exoplanet atmospheres, charting stellar neighborhoods, and measuring radiation fields are literally drawing the first versions of Starship navigation charts. The policymakers who choose to fund or defund space projects, the people who design international agreements on nuclear power, orbital debris, and space resources, are shaping how coherent and capable our civilization will be when it's time to talk about megaprojects beyond the solar system. Even outside science and policy, the role is real. People who strengthen education, keep societies relatively stable, improve healthcare, reduce the chance of large-scale collapse, and keep technological progress from derailing, all of them are indirectly affecting whether a 24th century launch window even exists. Interstellar travel won't be one dramatic switch flipped by a single genius. It will be the sum of millions of decisions spread over many generations, including yours. So when you ask, when will humans achieve interstellar travel, the answer is a rough window between the 23rd and 25th centuries. When you ask, does anything I do now matter to that, the answer is yes. You're living in the prologue, and the way this era handles energy, climate, war, cooperation, and curiosity will decide whether that first starship ever leaves the pad at all. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.